I, I do have that thing. I do, but I know I didn't spend as much time tweaking it as I wanted to, so I don't know about that. I know. Sorry to disappoint. No, thank you. No, thank you. All right, well, is everyone doing okay today? So I posted the solutions to the even problems from 7.1 on our website, okay? And I'll put the odd ones there later so that you have something to go off of. Did anybody have any questions over any of the homework problems? Preferably chapter 7, but go ahead. From 7.1? So if you have a book, let's see. We're looking at number 17. Is that the cosine pi x? Okay. Okay, let's go ahead and get started. I've been asked to go over number 17 on page 369, right? This is the one. And so the instructions, this section 7.1 is asking for the area of the region bounded by the curves. Sketch the region enclosed by the given curves, find its area. So I've got to know what cosine pi x looks like first, and then I've got to know what 4x squared minus 1 looks like. So cosine pi x. Any ideas? What does the pi in front of the x do? Changes the period, yeah, the period. So like if I plug in 0, I get cosine of 0, don't I? Which is 1. Cosine of 0 is 1. But if I plug in 1 for x, I get pi. Cosine of pi is negative 1. Good. So at 1, I'd be at negative 1 down here. And then if I plug in 2, I'm at 2 pi, right? And cosine of 2 pi is back up at 1. And then at the midway points, at 1/2, I get pi over 2. Cosine of pi over 2 is 0. So it's basically the cosine function where the period has been changed. And that's what you get. All right. Then I have, and it goes the other direction also, doesn't it? Maybe I should draw it this way also, like this. This would be -1 over here, -2 over here. Y equals 4x squared minus 1. That's a parabola, correct? Opens up, move down 1. So it starts here, and then it opens up. And I don't know where it hits. I'm going to do this one in red. I'm not sure where they hit each other, so I'm just going to kind of make it up. But at least I have the region, don't I? And I think it's perfectly suited for a rectangle in here that would be vertical, which means I'd want to be using an integral with dx, right? And I can see, I think, pretty clearly that I have a top and bottom function, if my drawing is correct. What's the top function? What's the bottom one? Cosine pi x is on top, so it'll look like this. Cosine pi x minus the other one, which is the 4x squared minus 1. And then this is the dx. Right, so that's still following what I've been doing, right? Okay. So the integral will be integral from a to b, which I still have to determine, right? Of cosine pi x minus 4x squared minus 1 dx. So we need a and b, don't we? We need to know where these two intersect. Where do they intersect? Excuse me? Negative 0.5 and 0.5. Wait. Where do they hit each other? Why are you looking at me like that?
Everybody's like figuring it out. I don't think they see it. But isn't it negative 0.5 and 5.5?
Well, that's from my drawing. It looks that way, but yeah, we have to set them equal to each other. I mean, from my picture, I just drew that parabola. I wasn't sure where they hit each other. So algebraically, to figure out a and b, I have to set the two equal to each other. Your calculator already told you? Okay, so right now I'm going to find a and b by setting cosine pi x equal to 4x squared minus 1. And yeah, this is obviously going to be the trouble part of this problem, right? You're trying to solve this for x, but what's wrong with trying to solve that for x? It's trapped in the cosine. The only way to get out of the cosine is to do arc cosine on both sides, but then now your x squared on the right side is trapped inside the arc cosine. So algebraically, there's not an easy way to solve this, right? It's not easy. So how about we just try something? Why don't we just guess? All right. From the picture, right, we can kind of maybe say we'll try something between 0 and 1. And let's do a number that we know will work. Like it'll be easy to figure it out when we plug it into cosine. Like let's try 1. Okay, let me just guess 1. I know it's not going to work, but let's just try. If x was 1, what would we get? Cosine of pi equals 4 minus 1. That's what I get if I plug in. That's not going to work, is it? Because cosine of pi was what? Negative 1 equals 3? No, that didn't work. So let's try something else. Another angle I know cosine of would be pi over 2, right? So let's try x equals pi over 2. Not pi over 2. No, not pi over 2. What do we want? We want it to be pi over 2, so what am I going to plug in? 1/2, right? If we plug in 1/2, that'll give us cosine of pi over 2 equals 4 times 1/2 squared minus 1, right? Cosine of pi over 2 is 0 equals, let's see, 1/2 squared is 1/4 times 4 is 1. 1 minus 1 is 0. So that works. You see that? It's like a guess and check. Unless you had a computer algebra system that would solve it for you. Or the graphing calculator using the intersect function. Is that what you did? Use the intersect function on the calculator. So, but this one would be more like an inspection. Is that where you were hung up on this one? The getting the A and the B? Okay. I won't give you anything like this on test. I'll give you something you can solve algebraically. And then what do you think our next good guess would be? Negative 1/2, right? Cosine of negative pi over 2 equals 4 times negative 1/2 squared minus 1, and that turns out to also be 0 equals 0. Did y'all see that? So A and B are negative 1/2 and positive 1/2, and that's it. The integral's set up. On the test, that would be the answer, and then the take-home part of the test will be to go evaluate it, to go figure it out. But the antiderivatives of that are pretty easy, right? Like, what's the antiderivative of cosine pi x? 1 over pi, just sine pi. So 1 over pi sine pi x. And then antiderivative over here, right? That's polynomial stuff. That's pretty straightforward. And then you just evaluate at negative 1/2, 1/2, and you're there. Does that help? Okay. Any others? Yes. Same section? Okay, number 13. Page 369. Thought I did this one. Hold on. I did, right? I think last class I did that. Yeah, it's in here somewhere. You got it? Okay. Any others? Oh no, that would, yeah, would have been back. Others? Anything from last time? From the revolution? Anyone get to the homework for 7.2 yet? No? Okay. Well, that's what we're going to pick up today. Remember that the 7.2 will be our last section on the test, all right? 7.2. I decided that's where we're going to end it. Now, what we were doing last time is we were finding regions between two curves, and we were revolving around the x-axis, right? And then we revolved them around the y-axis. Then we revolved them around a line x equals something, and then a line y equals something. We never did one of the y equals rotations, right? So that's what I would like to start with. So I'm going to go out of the book, and I'm going to do a problem here, something that goes around y equals something. So how about, I'm going to try and get an even one so I can leave an odd one for you. Where's the one? I looked at one before class here. Hold on. Okay, here we go. How about we want to take the region x equals 2y minus y squared, or there's one curve, and then the other is x equals 0, and I want to revolve this or rotate about the line. Let's start just to warm up. Rotate about the y-axis. Let's just start with this. So we're going around the y-axis, right? So let's start by doing what? I mean, what am I expecting for you to show me on problems like this? A graph, right? Show me the region that's going to get rotated, right? So graph the region first. X equals 0, that's the easy one to graph. That's just the y-axis, right? That's x equals 0. And then x equals 2y minus y squared. That's a parabola open sideways, doesn't it? Which way does it open? Like to the right or to the left? To the left, because it's a negative on the y squared. So you could plug in some values if you wanted to try and figure out, you know, like what is, like plug in 0 for y, what do you get for x? Right? 0 for y, you get 0 for x. That means I should have a point on there. If I plug in 0 for y, I get 0 for x. So that's the origin is 1 point. Let's plug in another point. One, plug in 1. 1 for y, right? Plug in 1 for y. What would you get for x? 1? Yes? Okay, so 1, 1 would be a point like right here. How about the next point? How about 2? What happens if you plug in 2? What do you get? 0 again, don't you? Plug in 2 for y, you get 0 for x. So something like that. Or just use your calculator and you get the rest of it, right? Looks like this. Like this. So the region enclosed by both is the region right in here, right? Correct? And we want to rotate that around um, the y-axis, which is the blue line again, isn't it? Okay, so which way is our rectangle going to be facing here? Sideways. I'm going to blow this up here so I can get into that rectangle. My rectangle should be in here, should be sideways like this, right? And then I'm going to revolve it, right? I'm going to revolve it. So it should be, remember what we were doing last class, we were trying to act like we were standing on the axis of rotation, looking out and saying what's the outer and the inner, right? So what's the outer function for me if I'm standing looking that way? It's the red one, which is the 2y minus y squared. And then what's the inner function? X equals 0. Yep, yep. Right to left. Right is the outer, left one is the inner. Okay, so the formula we had kind of from last time was that we're basically going to have an integral here. It's going to go from C to D because we're going horizontal rectangle and we're revolving this way around the y-axis. Pi, don't forget the pi, right? Say again? Yeah, we have C and D, but and then we have the what? But it's the outer one squared minus the inner one squared. Not outer minus inner, then square the whole thing. It's outer squared minus inner squared. So the outer one here for me was the 2y minus y squared minus the inner one, which is just 0 squared, and then dy. And then yes, our limits of integration, our d is the top one, our c is the bottom one, which are what? 0 and 2. So it should be 0 here and 2 there. And that's the basic setup for the integral. Questions?
That's what you're gonna want on the test?
Yes.
Could we pull out the pi?
You could pull the pi out front, that's fine. You could not write the 0.
When do you know to put a pi in front? Is it only on these?
only on the only on the solids of revolution. If it's area, it's not squared, and it's just F minus G. That's it. Yeah. Just remember, when you rotate, you're creating a bunch of disks, and those disks contain circles. Circle pi r squared. So you have the pi in there, and you have the radius squared part. Okay. Let's do the same problem, but I want us to do it over a different axis of rotation. So the next one, let's take x equals 2y minus y squared. Take x equals 0, and let's rotate it about x equals 5. Same picture, right? At least the parabola thing we have. Yeah, there's a couple of differences now. We've got that parabola. We've got the blue function still here. It's still the same region that we're going to rotate. The difference is where we're rotating. And we're rotating along the line x equals 5, right? So I'll do this one in green. 1, 2, 3, 4, 5. So there's 5. I'm going to draw a dotted line. And I'll do my little arrow, circular arrow there to show my rotation. And we spin that around, right? It's what it always sounds like at my house. Our backyard is like, the back of the house is like 15 feet off the ground, so all we have are trees. And then birds come through, and it's just, it's like every day we get a bird. Yeah. Okay. Well, so you're still doing these little rectangles in here that are horizontal, but stand. I'm going to put my little man standing. He's standing on the axis of rotation in blue, right? That's where I'm standing, and I'm looking out towards my rectangle laying on the ground there, right? I'm looking out, and I'm asking myself, what's the outer radius? X equals 0 is the outer function, but how far away is that from me? That's 5 units away from me, and it's always going to be 5 units away from me. So it's 5 squared. You see the major difference here? That's what I was trying to get to at the end of last class. Is it's not about what the function is necessarily anymore. It's the actual radius from your rotation line to where you're rotating, and that line is never changing, so it's always 5 units away, right? So if I spin that around, it's always 5. That makes sense? So the outer one, I'm going to label it here. The outer goes from here all the way to here. This is my out, and it's 5. Okay, now the inner one is the distance from the inside of that rectangle to my axis of rotation. Yeah, what is it? I mean, well, it's 4 at this point, but isn't it changing? Like if my rectangle moves down here, that's not 4 anymore, is it? It's changing, isn't it? So what's the distance? Maybe it's better to look at it, the distance from here to here. What would that be? It's 5, right? 5 is all the way. And how much are you taking away from it? That much, right? And what is that much? The equation. So it's 5 take away 2y minus y squared. Is that, yeah? So the distance here for the inner part, or the inner radius, is the 5 take away the 2y minus y squared. which is just 5 take away 2y, add y squared. I just distributed the negative through. Yeah, this is just that's just the distances. Now I go to the formula, it's outer squared minus inner squared, pi in front. Okay? So all the setups on these are pretty much the same. I mean, the challenge first is get the region to look right, and then stand on your axis of rotation, look out, what's your outer, what's your inner, make sure you've got that all taken care of, and then write the formula. We still have C and D, right? And it's still 0 to 2. Now, pi outer squared, 5 squared, minus inner squared, 5 minus 2y plus y squared squared, dy. What's that? You got it? Okay. Now, if you were going to integrate that, I mean, how would you integrate this thing? I would actually just multiply that all out. Like, take that, square it, times itself, distribute. It's a polynomial. Then you can just do integration term by term, antiderivative of each one. Now, let's just, so we kind of really understand how important it is where that axis of rotation is and how it changes the formula. Let's put that line that we're rotating, let's put on the other side. So let's go x equals -5 now, so we can really see kind of the contrast. So taking the same x equals 2y minus y squared, x is 0. We want to rotate it about the line x equals -5. Why don't you see if you can come up with it? Let's see if y'all can convince yourselves of what the formula for this would be. Stand on your axis of rotation, look out. What's outer, what's inner? Who's going to go out on a limb here for me? What do you got? Give me the integral.
The integral from 0 to 2 is pi, brackets, 5
Anyone agree? No? We got some disagreement?
That was what our table said.
This table agrees to that or no?
Yeah, we all came to that conclusion.
We also agree.
You concur?
Unlike our parentheses, that's like a parentheses, I don't really like.
Okay, so I get some looks of
What about 6? Oh, wait.
6.
Yeah.
Because the first part is 6, closest is 5.
So we have some disagreement here then.
But the function itself is 5 away from it.
Okay, let's start by saying how many of you agree with this? Let's just see hands, okay? And disagree? It's okay to disagree. Okay, I just want to kind of see where we are. All right. So, does anyone that disagrees want to tell me what they think it is? Okay. Put negative 5s here. And then anyone else want something different than that?
X equals 0?
X. No one has anything different than that?
What about 6 minus 2y?
6 minus. Where's the 6? Where are you getting the 6 from?
You measure
You're
5,
standing at -5, right?
and then it comes out 1 to the right.
Okay, so here's our picture, right? Same thing? And our axis of rotation is over here, right, at -5.
Right.
And our rectangle is in here, as it was before. And so if I'm standing on the axis of rotation here, right, and I want to look out, and I want to know the distance from myself to the edge of the rectangle, from here all the way out to the edge of the rectangle, what is that distance?
5 plus 2y.
It's the distance from me to the y-axis, which is always going to be what? 5, right? That's always going to be 5. Not -5 because it's a distance, okay? And then I have to tack on the rectangle itself. And the width of this rectangle depends on where I am. Like if I move this thing down, it's not 1 wide anymore, is it? The width of this rectangle depends on where I am, right? So the width of that rectangle is the height of that function, which is the 2y minus the y squared. Okay, so that other little piece right here, this distance right here is the 2y minus the y squared, right? So that whole distance, all the way, this whole distance is the 5 plus the 2y minus the y squared, right?
So I wanted to put it in different parentheses, that way you can see it's like the
Yep.
distance and then like the function itself.
And then the 5, yeah, that's good. I was wondering where you're going with that, but then once you wanted the parentheses on the far outside, I saw it. Okay. Questions on that? That okay? Now, what about the inner radius, the inside? That's always going to be the same. So if you slide that rectangle up and down, the bottom of that rectangle is always the same. It's always 5 units away. So 5. And so this integral is correct. You would have the 5 here is this part, the greenish part here, and then the blue part is all of this. So you got pi times the outer distance squared minus the inner distance squared, inner radius. Did that help with you doing that one yourselves? Okay.
And then that's the answer? That's what you want on the test? If that wasn't
Yeah, yeah.
So you take it home.
I'm curious how you would deal with this one. Let me see. Watch, what about this one? X equals y squared minus 2y, x equals 0, rotating it about x equals negative 5 again. So I changed this function a little bit, all right? You'll see that? I changed that one to be a y squared minus 2y instead. So I have to kind of do a different graph here, don't I? My graph is going to be, let's see, let's plug in some values. If I plug in 0 for y, I get 0 for x. If I plug in 2 for y, I get 0 for x. If I plug in 1 for y, I get negative 1. So it's basically that same parabola flipped over, isn't it? Do y'all see that? I just took it and flipped it over. And now I have x equals 0 again. And I want to rotate it around y equals negative 5. Or sorry, x equals negative 5. So I still have that rectangle. It's still sideways. I like that. I'm happy about that. I think on this one I'm going to somewhat exaggerate where I place my rectangle, because I think a lot of people are getting kind of stuck on the idea that the rectangle has to be in the middle or something. That rectangle is moving, remember? Because we're taking infinitely many of them, right? There's infinitely many, and we're adding them up. So that rectangle is never fixed in one place. It's arbitrary. Okay, you ready? Talk about the outer inner. I'll let you do it. How about you take a minute to do that? See if you can come up with that one.
Formula?
Yep, the formula for it.
Because you see the axis, like that dotted green line, right? You're taking the distance from that green line to the functions.
Okay, take a push ice and flip it around, it comes all the way around the thing.
Because that line is further, it's like you're 5 and then the line. Yeah, that's why the last one you added, like this one. But see, the reason why you subtract is because it's 5 to the y-axis minus where that red line takes you. Because the red line is on the left side, which is, if you subtract this, is a negative, and the right side is a positive. But you're not rotating around the
Yeah.
y-axis.
Yeah. Yeah, because you obviously minus.
You're not, we're not rotating around the
All right,
y-axis.
are y'all ready?
We're rotating about
Yeah.
that x equals 5.
All right. I'm not gonna. I'm not gonna let you volunteer. I want someone else.
I'll do it.
You you want to go for it? Well, I want the whole integral. So,
It should be the integral from 0 to 2,
okay, y'all ready? Here we go. Integral 0 to 2.
and then you can put a pi outside if you want, right?
All right, pi.
And then open bracket, parentheses,
Okay,
5, and then squared.
Okay.
minus parentheses 5 minus y squared plus 2y, and then close the parentheses
Around the y squared plus 2y?
after
Or
the 2y, and then square that, and then close the bracket, and then dy.
You distribute.
okay. Agree, disagree?
I concur.
So how many agree with this? Yeah? So there's something in here we need to talk about to make sure everyone's clear on it, all right? The outer one is the easier one because you go from your axis of rotation to the outer part of the rectangle. That's going to be the distance from here all the way to the outside, which is stuck at 5 the whole time, isn't it? So your outer is 5. The inner's the tricky one because the entire distance, even if you got this right, okay, please pay attention. The distance all the way is 5, right? But we want to take away this much, don't we? But you don't subtract it. You don't subtract the function there. Why not? Did you subtract the function?
I did 5 minus the function.
That's not right. What you told me to write is correct. But 5 minus the function is not correct. 5 minus the function is not correct. Why not? The function takes on negative values over here, doesn't it? Right? So look, just for example, if I pick the point where my y coordinate is 1, right? When my y is 1, what's my x value? X is -1, isn't it? So I'm right here at this point. How far away would you be? With this rectangle right here, how far is the inner distance? 4, right? It's 4. Now if you had done 5 minus the function is y squared minus 2y, isn't it? Now it needed to be in parentheses for that minus to go through, right? If it's 5 minus the function, plug in y equals 1 into this right now. Plug it in. What do you get? 1. Take away that. So that's a -1. Minus a -1 is +1. That's 6. So that means that the inner part of the rectangle is 6. It's not 6. It's 4. So because this is 5 and this lies on the left side of the y-axis, these are negative x values, aren't they? They're negative x values. So you want to take the 5 and add that negative value to get the 4. Hmm? Hmm? No?
But my question is, if you okay, the negative sign plus.
This should be a plus.
Yeah, that should be. Yeah.
So in the second part, are you gonna like distribute a negative?
No, it's not distributing the negative.
That's what he did, and it came out to be the right thing.
Yeah.
That's what it seems like.
Got lucky.
Like,
Matrix.
No, because I didn't distribute a negative. This is correct. Hold on. Minus. Hold on a second.
That's right.
Yeah, I distributed the negative.
This.
You can't distribute the negative.
Let me write down. I thought the integral what he said was right, but now that I look at it, that's not right.
That's 5 plus. 5 plus.
That's not right.
Yeah.
Let's write the inside out. I'm sorry. I thought that's what. Okay, so this should be 5, and then you want to add to it, right? The function which was y squared minus 2y. Not subtract it. Not subtraction. And then when you come down into this, down to, let's fix this integral now. What should this read? 5 plus y squared minus 2y. This is a really, really important example. Does anyone need clarification? This is important. I don't want you to fumble this up because on a test, it's going to cost you big time if you don't do that correctly. You might be like, oh, it's only a sign. I mean, it's the fundamental ideas here. Yes. Okay, yeah, I will. Maybe it'll help. Maybe it'll help if I start kind of from scratch and I just do a picture like this. Let's say I have, well, you know what, let's do this. I'm just going to make this the function or the curve y equals x squared minus 1. And I'm going to draw a line down here at -4. Okay? Then can you tell me the distance, just in general, can you tell me the distance between here and here? The exact distance between this point and this point right now? 3, right? That's 3? That's 3? Because it's the total distance from here to here, which is 4. But you want to take away what? 1. Now, if you look at that function and plug 0 into that function right now, up there, for x, what do you get for y? -1, right? So if my x is 0, my y is -1. How can I take the 5 and put it together with that to get my, or wait, not, it was 4, right? 4. I need to add that value because it's a negative value. So when I add the negative, it'll subtract. I don't know if that makes sense.
Yeah, it's 'cause it's
You
negative.
add it no matter what, because if you add it and it's negative, it's gonna subtract it.
That's right. I'm adding it because it's negative. Now what about this? What if I do this? I put the function above now, like this.
Oh, you broke it.
It's the same thing, but the distance changes.
What's the difference?
You're gonna add
It's
it,
not
but
negative
it's
now.
positive, so it's gonna get bigger.
Is there a difference? It would still be, what were we trying to say? We were trying to say from here, right? The distance would be 4, and we were saying we wanted that to take it away, so we added that function. Well, if we want to go from here to there, what? You got to add it anyway, don't you? You got to go 4 and then add that function. So for both of those, it's the same thing.
Same thing, the constant changes in the motion.
Yeah, so every one of these problems is kind of unique. You have to be able to understand the geometry of what's happening. You can't just, like cookie cutter stamp, this is what you do given every situation. You have to look at it, understand it, come up with a formula. That's much more profound than just like, if you see a graph on top and a line below, then do this. And if you see this and this, and that's not the way to do it. You think it through, all right? All right, those were kind of fun. All right, so I think we've got the whole idea. Hopefully, I don't know if that helped. If we can clear it up some more, with some more examples later. But I think that does it for the rotations around the x-axis, y-axis, horizontal and vertical lines. All right, for now. Now in this section, they kind of finish up with this last topic, which is somewhat weird. I never showed you my thing that I promised I would bring. Let's see if I have it here.
Just searching your whole class based on this presentation. I go do mine. So is good in the class? This is good.
Teacher reviews.
I don't remember where I put it.
Bad teacher reviews it.
It's not with my professors.
There we go.
Pressure.
Well, this was pretty much it, and whoa, what the heck is that? Oh, it's down here.
Like, the worst rating possible, he was like, this is all true. That's awesome.
So
If you want to drop it down, go for it.
this is a sine curve, and we found the area under it before, right? And now we want to revolve it around the x-axis. So my little demo was just a decent it's a decent way. Ooh, man, it's a little harder than I thought it would be with this. Okay, so you just take it and you just, you flip it around like this, and then You can kind whoa, I have very little control with this thing. You can kind of see the two like football shapes there, right? That's pretty much it. I'm not going to, I had more, but I'm not going to go into it. I think everyone at this point understands what's happening, right? Yeah? Okay. Okay, so now we're going to start this next thing, and man, I'm telling you, these are weird problems, but I think if you can catch on to it, it's cool. Forget the whole idea of a function revolving around an axis, all right? Forget it for right now, all right? And think about instead how we came up with the formula for it. Do you remember how we did it? We took the curve, made a rectangle, spun it around, and said that's a cylinder. Then we came up with the formula for a cylinder, didn't we? And we used pi r squared times h. Okay. The way we constructed that formula is what we need here today. So I'm going to read you one of these problems, and then we'll try it. This is going to be on page 380, number, what should we do here? 42. Does everyone have a book, or someone around them have a book? I'm going to read it to you. The base of S, the base of a solid, is the region enclosed by the parabola y equals 1 minus x squared in the x-axis. Cross sections perpendicular to the y-axis are squares. Find the volume of this solid. Yeah. So here's what we got. We have the base. There's some solid that we're trying to find the volume of, okay? But it's not a rotation thing. It's just some solid. And here's what they tell us about the solid. The base of the solid, so I'm gonna make this the ground, okay? We're looking straight down on the ground. The base of this solid is the region enclosed by the parabola y equals 1 minus x squared and the x-axis, which is y equals 0, right? So if I take my solid object, whatever it is, right? I put it down on the ground. Where it's touching the ground is the region bounded by those two, all right? That's what we have. So now I'm basically drawing kind of like the shadow of it down on the ground. Just the bottom of the solid, that's all it is, okay? So 1 minus x squared looks like this, right? Parabola, and it hits there at 1 and negative 1. And then the x-axis is my other little piece here. So that's my y equals 0. And this region inside here, right, all this in here, that's the base of the solid. Okay, that's the bottom of the solid. So it's, I mean, you could look at it as take a Coke can, right, cut it in half, set it on the ground. Wouldn't it look like that? If I set that Coke can cut in half on the ground, that's what it would be. But I'm not telling you it's a Coke can. Do you have a question? No? All I know is that's what the base of my solid looks like. All right? Okay. Now, I'm read on in the question here and see what else it's telling me. It says now cross sections. That means if you take this solid that's above here and you cut it, all right? Cross sections that are perpendicular to the y-axis are squares. Cross section means perpendicular to the y-axis means what? Here's the y-axis, perpendicular would mean like this, right? So if I take this thing and I cut it like that, like let me just get like a razor, cut this thing off, take it and look at it, what geometric shape is it? It's a square above that. Okay, so that means that I'm going to give you a better visual of this, but before I do, I just want to see how much we can do with this. That means that if I take this front edge right here, and I take this corner and this corner, then that distance is 2, right? That means that above it, there's a square that's 2 up, 2 over, and 2 down. Do y'all see that?
Yes.
But if I move back a little bit, what's the distance between these two? Less than 2, right? And the square above that one is a little bit smaller than the one in front of it. And then I take the one behind that, and the square is even smaller. And I go behind that, and the square is even smaller. Y'all see how that works? So what would it look like? And what's its volume, more importantly? Yeah. Yeah, so let me try we're about to go 3D now, okay?
Where so it's different. Like the top of your shoe goes down like that.
There's my XY
Rectangle shape.
and Z axis.
It's like that.
Now what I'd like to do is try and draw that same picture I just had on there. So the ground is the X and Y right here, right? And then Z is three-dimensional coming out. Do y'all see that as 3D? Okay, so I'm going to actually extend my X-axis out the back. And then my parabola would look something like this. Right? On the ground? Actually, I don't really care for that part right there. I'll probably never be able to reproduce it that well again. But. Whatever. You get the idea, right? That's the base of my solid. Then I'm going to take this front edge, those 2 points we said the distance between those were what? 2. And I'm going to create a square that's 2 units high, 2 units over, 2 units down, right? Then I'm going to take another 2 points. I'll pull them back here. And I'll make that square has to go however many units that is, and over and down, right? And I have infinitely many squares. So my next 2 points, like here and here, I go up, over, down, right? And I could actually even connect these corners together, and they all come down to a point there. And these corners come down like to a point like this. And you get some weird looking three-dimensional shape, right? Okay. How many of you are taking Cal 3? No? Not anymore? Okay. Well, or becoming an engineering thing. You just get used to being in three-dimensional space because we live in it, right? So, oh man, what are we going to do here? The idea that we've been using, right, is to basically take these things, find a formula for one little sliver, and then add them up forever, right? So can we get a formula for one little sliver of this? I'm doing it in red there. Just one, and I'm going to make it just give it a little bit of width. The width is the dx, right? The dx is a little bit of width. And let's take that over here and take a look at it. How wide is it, that little sliver? Dx. Okay, we got all that. Well, wait, hold on. Is it dx? Is it dx? Look at your ground. Look at the thing on the ground, right? The bottom of this rectangle down here, or this thing. What the width is, that rectangle on the ground is,
Which one? Like,
which variable is it? Dx, dy? Go back to this picture right here. Our rectangles that we're drawing are going sideways, aren't they? Like this? Aren't they? Going sideways? So isn't that dy? That's dy, not dx.
The length is dy?
So this is dy, this part right here. This little edge is dy. Do you see that? No? What?
Didn't our rectangles go up and down?
They do go up and down. I'm not sure I understand.
The way that that's rotated is like confusing me a little bit.
Yeah.
The way's what?
The way that when you drew it three-dimensional versus the one-dimensional, that's what kind of.
Well, you have to be looking like for this, you have to be like standing on the like this. Look, the x-axis comes this way, right? The y-axis goes that way. So if this is the x-axis and this is the y-axis, my parabola went like this, didn't it? So if you stand up like this and look at it, here's your parabola like that. That's what we're doing.
Why are the rectangles horizontal?
Because of the picture. Again, if I'm looking down like this, right, my y-axis is going this way, my x is going this way. So if this is my y-axis, this is my x-axis, and I'm looking down on it, and I'm drawing my rectangles like this and coming up with them and creating my square, then that little sliver on the ground is running horizontal, not vertical. So that's dy. We need to know how long this thing is. How long is that? I think what I'm going to do is I'm going to draw right under this. I'm going to draw the same picture in two-dimensional. So here's my little parabola thing here, right? And my little rectangle inside that's on the ground goes like this. It's x and y, right? So that's looking straight down. How wide is it?
Well, how wide that is the
It's
distance between the 2 points of f of x.
That's right. The problem is that what we've been doing with our functions is that when we did our rectangles this way, we did them this way because the top and the bottom were different functions, weren't they? This one is the same function. So we can't do it the other way though. We can't cut it vertically because they're not saying that their square is going this way.
Yeah, but I'm saying the distance is. Keep going.
Yeah, we need this to be a function of y, not a function of x. We need to be a function of y, not x, right? And we can use the symmetry that the volume above this side is the same as the volume above this side, isn't it? I knew that's where you were going, but so what I'm going to do, all right, is I'm going to say, let's look at just this right side, just that parabola coming down, and just the rectangle going this way. And can someone tell me what this blue thing is as a function of y? Like x equals what? Well, they gave you the function in terms of y, didn't they?
Yeah.
So can you get that in terms of x?
Yes. Square root of y minus 1.
Square root of 1 minus y. Take the negative x squared to the left. Take the y to the right. So you get square root of 1 minus y. That's what x is. So isn't that how long that rectangle is? I mean, the distance from here to here is basically the height of that function looking to the right, right?
So will be 2 square root of 1 minus y.
Yeah, so now I'm going to go back up to this picture here. We said how wide was that thing? It's 2 of those, right? It's 2 of those. So it's 2 square root of 1 minus y is wide. Isn't it? And then how tall is it? It's a square. It's a square. They told you in the problem it's a square. So it's 2 square root of 1 minus y. So what is the volume then of that one little sliver right here? The volume of a rectangular solid is length times width times height. So 2 times 2 is 4. Root of something times itself is, the root goes away, you get 1 minus y dy. That is the volume of one sliver. What do we need to do? Add them up, right? Add them all up. Integrate it. From where to where? Yeah, on your y, it's from C to D, isn't it? So it's from 0 to 1. So you're going to go integral 0 to 1 of 4 1 minus y dy. That gives you the volume of that solid. That's kind of weird, huh? Bonus.
Oh yeah.
Okay, let's take a look at this. What I've got here are two parabolas laying on the ground. Can you see the blue and red parabolas? So they're like, they're like this, right? Laying on the ground, two parabolas. They have a region between them, don't they? That is the base of the solid, the green solid you see there, right? Above it, perpendicular to, this is the x-axis here. This time perpendicular to the x-axis, cross sections are squares. So if I take this and I cut it, do you see the square right there? Do you see that square? And then another square right here. And what I can do is I can pull the actual surface out. That just looks like a wire mesh of hell. But if I spin this around and we look at it from this side, oh, you can kind of see the squares. Kind of, right? You can see those squares in there? Now, but there's nothing that says I have to have a square. I could put a circle above it too. Now, instead of coming up and making a square above this, square above it, square, make a circle where the distance from here to here is the diameter of the circle. So if I do that, I get that shape. Or I could do half circles, right? Or I could do triangles. See, if I come in from the side, do y'all see the triangles in there?
Why would you want different shapes?
Okay, one classic problem of this is, let's say you have, and I wouldn't give this to you, all right? But let's say you have two pipes that come together. Okay? That's two, like, let's say two water pipes that come together. And they kind of look like, okay, that's the way two pipes would come together, right? What's the volume of the water, or whatever's in there? What's the volume of the water within their intersecting parts? Now, when I say that, I mean, what's the volume of the water in this part of the pipe only? So, you'd have to cut this end off, which would leave you with the little circle over here. Cut this end off, which would leave you with the circle over here. And then cut this end off and cut that, right? Inside there is a weird shape, isn't it? And that's a very, very odd shape. Do y'all see that? Because the way this comes down and the way this one comes up and the way it all goes together, I mean, you can't just say, oh, it's the volume of this way and then just subtract. I mean, there's nothing easy. It's an awkward shape. And you can get it by using this, what I'm showing you. If you can describe what the base of that solid looks like and what all the cross sections above it look like, you can get the volume. And then what you can do, I mean, later on, like if you take Cal 3, if you take it with me, we're definitely doing that problem. And then we're also going to we would also figure out like the distance. If you were to try and tie a rope around this to go from here all the way around to the other side, like what's that length around those two? So yeah, there are applications to finding the volumes of odd looking shapes, but that have some sort of common symmetry to them. So we'll try one more, and we'll probably be done. So I'm going to kind of make this one up, all right? Let's say that we have a region, or wait, a solid has a base which is region bounded by y equals 4 minus x squared and y equals 2x squared. Cross sections perpendicular to the x-axis are triangles, or sorry, equilateral triangles. What's that? Equilateral triangles. Find the volume of the solid. Are you ready? So the first thing you should start with is the picture of the region that's the base of the solid. So what's the picture of the region that's the base of the solid? Do y'all have this written? Are we good? Okay. What's the picture of this? 4 minus x squared starts up here at 4, cuts through where? 2 and negative 2, right? So we've got this guy comes down like this. Ooh. Comes over here like this. Okay? The other one is 2x squared. So that's a parabola that opens up. It's somewhat steep. The region between them is obvious, I think. Cross sections perpendicular to the x-axis are triangles. So when I come in here with the, whatever, sword or whatever it is, and you cut it perpendicular to the x-axis, like this, whoosh, and you take that little piece off and look at it from the side, it's a triangle, an equilateral triangle.
That means the points are evenly dispersed between the two, correct?
That means that the well, let me do it this way.
So shouldn't it go from -3 to 3?
What's that?
The first problem, 4 minus x squared.
No,
Negative.
-2 to 2, right? 2x,
That's what my calculator says.
what, 2?
Two. Yeah.
4 minus 2 squared is 0,
Yeah. Okay, so 2.
right? 4 minus -2 squared is 0.
Next time you get the best.
All right, do you want me to draw would you like the three-dimensional one now, or do you want me to kind of give you the idea of where's the rectangle now? I mean, what makes more sense to you? Like, where's the dx, dy, or
So it's dx.
it's going to be dx, because I'm cutting this way, which means that wherever I cut,
It's gonna be along the x-axis.
it's going to be like this,
Yeah.
right? That's my little cut. And when I take that green thing out and look at it from the side, it's a triangle, isn't it? So I want to do my 3D here. I have to do it below it. Remember, when you go to 3D like this, the floor, it's kind of weird. You're kind of looking at it from the side, right? I have my, which one was it? The red one went from the origin, so I have my parabola on the ground coming up like this. Then my blue one started up at 4 and went down. Not very good. That's okay, I guess. It'll work.
Yeah, it's right. So you just come out more on this side.
So my cut on the bottom, that rectangle is like that, isn't it?
Yes.
And that should be one length of one side of an equilateral triangle. So imagine from that right there, if that's the base, right, then I have a triangle made out of it, like this, and it has some width to it, right? That's what's happening there. Isn't that what we got? What's, yes, that, okay.
Somebody say yes.
So what's the sort of about?
I was imagining like this shape
Trying to
of
figure out
my
what it
head.
looks like.
Oh, yeah, what this looks like? Yeah, it's going to be odd. Pretty weird.
That's what I'm.
Well, it's actually this. I mean, it's this one right here. It's pretty much that.
Yeah, but the way that it's shifted is what makes it look funny.
Yeah, those parabolas are the same.
Those parabolas are the same and mirrored over the x-axis.
Yeah, but imagine the axes aren't even there.
Yeah, but one is like pointy and the other one is not. It's equilateral triangle. See how those two have the same like slope?
You're saying they look exactly the same, like the same parabolas just reflected. Yeah. So it would look a little different.
Yeah, so it's like.
Where's the
Yeah.
bridge going?
It'd look a little different.
Yeah, that's what
I can't tell you because I don't have it.
I'm like imagining it myself.
Yeah.
I think it's made of how many.
Okay. Can we talk about this? The volume of that thing? How wide is it? dx, right? dx this time. All right. What is the? Don't we need the area of the triangle and then just multiply it times dx and we have its volume? So what's the area of an equilateral triangle?
Times base times height.
1/2 base times height, but we don't have the height. We do know the base though, don't we? We know how long this is. How long is that? Ooh, how long is that?
That is.
Doesn't my blue function come in over here somewhere and my red function's the one on the bottom? Right? My triangle is like right in here. I kind of wanted to take it out of the picture to make it less confusing, but you bring that out here, That distance is the difference between the two functions, isn't it? So it's the top one minus the bottom one, which for us is the blue one minus the red one, which is what? 4 minus x squared. So this is 4 minus x squared minus 2x squared, which is just 4 minus 3x squared, right? That's how wide it is. Now, there are two ways to find the area of a triangle. There's area is 1/2 base times height. Anybody know the other one? No. 5-point bonus on the next test right now. The other formula for the area of a triangle, other than 1/2 base times height. Oh.
It's 1/2 AB sine.
Sine.
He's looking at his formula sheet.
Hey, but he knew where to go.
They Google this real quick. The side of the angle.
Sine of the angle. That's pretty darn close. So it looks like we need a little quick refresher here. This will save you a lot of time if you know this formula. If someone gives you a triangle like this, and you have the height and you have the base, then the area, of course, is 1/2 base times height. I mean, my college algebra students know that. Okay? But if you don't have the height easily available to you, you have to compute it, which takes some time. I mean, the only way we can get the height of our triangle, right, because our height's right in here, the only way we can get the height is to do a little right triangle and do a little Pythagorean identity, because we know the length of this side is this, and we know the length of this side is half of it. So we'd have to go a squared plus b squared equals c, or wait, no, sorry, a squared plus b squared equals c squared, and and you could do it, but it's just a little more algebra than you really need to do if you know this. If we take that same triangle and instead we know the angle and this side and b, then the area is 1/2 AB sine theta.
You said that.
That's what he said. I didn't hear.
So it's 5 points, right?
When did you say it? After he said it? I didn't hear it.
Oh, I thought it was 5 points for everybody.
I get it.
All right. We'll work it out. I'll consider the two of you because you were resourceful and you didn't speak loud enough. So we'll work something out. Okay. Now, how many of you have seen that formula? Now that I've put it up on the board, you seen it? Physics. Okay. Now, look, just because I don't like things to be voodoo magic, there's nothing to this formula. Tell me real quick, sine of theta. Look at this triangle over here. By definition, what is sine of theta? Oh, it's what over what? Opposite over hypotenuse. So what would it be here in this particular triangle? It would be h over a, wouldn't it? So this is really just h over a. And then we have a, b, 1/2. And then what cancels there? The a's. And what do you have? 1/2 bh, which is, so another way you could get this formula is by doing this, saying, hey, look, see this formula right here, the h? Tell me what h is. Well, if I know this angle and I know this side, then I can define a trig function there, and then I can substitute the h out and replace it with sine theta. That's all it is. But it's so useful when you have an equilateral triangle, because you know that all the angles are pi over 3, 60 degrees, and you know all the sides. So you have the A and the B are the same. So what would the area be? I want to get this done so we can get out of here. What's the area of the front of that triangle? Just the area of the front. 1/2 AB. What's AB? They're the same, aren't they?
Yes.
A and B are the same? So it's A times itself, so squared, times sine of 60 degrees, which is root 3 over 2. So root 3 over 2. So the area of that little piece is root 3 over 4, 4 minus 3x squared squared. And so the volume of that sliver, of the sliver, is just that thing with dx thrown on the end, right? And then finally, the volume of the entire object would be the integral. From where to where, though?
For everything. Set them equal to each other.
So you'd have to figure out where they hit each other, so you'd have to set them equal to each other. Okay? So I'll put the final integral, but I won't put what it, I don't know the limits of integration. Do we want to try and solve it real quick? Is it easy? 4 minus x squared, maybe, hold on, 2x squared. That's what we're trying to solve. So 4/3 equals x squared, so it's, what, 2 over root 3? Positive and negative 2 over root 3? 2 root 3 over 3? Two root 3 over 3, but that's if you rationalize the denominator. 2 root 3 over 3 and positive and negative, right? And then now you have the formula we just came up with, which is root 3 over 4, 4 minus, what the heck was it? 4 minus 3x squared squared dx. If you can figure out the antiderivative of that, then and then plug in, then that's the volume of that crazy shape. All right. Well,
Pull the square root 3 over 4 out.
yes. Yeah. Okay. So we have like 12 minutes. So you want to talk about the test?
Yes.
All right. So here's what I'm planning on doing. I will be here the rest of the week if anyone wants help during my normal office hours. Saturday, I'm giving an internet exam that goes from 9 to 12. So I'll be here from 9 to 12 on Saturday. It's not going to be like I can give like one-on-one personal tutoring, but if y'all have a study group that wants to get together on campus or something and wants to come hang out in my office area, and if y'all get stumped, I'm going to be there from 9 to 12. Okay, so you work out whatever, but I just don't want anyone to be disappointed if you show up and I can't just sit with you the whole time. So I'm going to have students running around everywhere. All right. So I haven't made the test. Like I said, I haven't taught this class in like, I don't know, 5 or 6 years. So I don't have an old one that I even want to look at to go off of. So my idea here is to just start with chapter 6, right? I'm going to go through the integration by parts section. I'm going to pull a problem. I mean, not like a problem exactly from the book. I'm just going to look through and I'm going to say, okay, that looks good. I'm going to pull one, something out of 6.2. Now in 6.2, there's trig integrals and there's trig substitution, right? Trig integrals were like, sine cubed. Where you might have to do like a factoring out of a sine squared and a power reduce or something like that. So you'll have something like that. And then you'll have a trig substitution problem where you'll have to do like, replacing your x with, a sine theta or whatever it is and doing that. So that's 3 problems. Then I'm going to go and I'm going to do a partial fraction problem. I'm going to make it a pretty basic partial fraction problem. I'm not going to get crazy and have like, repeated linear factors with repeated linear quadratic, or quadratic factors. And I just want you to show me that you got the gist of it. And well, I mean, you'll use your calculator for sure, but I mean, I'm going to have them probably I mean, I wouldn't be surprised if you could do the elimination, get your A, B, and or whatever by just doing that trick where you just, not trick, but where you just said let X be this and wipe out the others. Right. That's 6-3, partial fractions. So 1 from there, maybe 2, but probably 1. Nothing out of 6-4. That's the table of integrals stuff. 6.5 we didn't talk about. Okay, 6.6, improper integrals. There are 2 types of improper integrals, right? There's the type where you're letting your limits of integration become infinite, like going from negative infinity to infinity, something like that. That's one type, so you'll have something like that. And then the other types are where you have a discontinuity. So like you're integrating from, let's say, 1 to 4, but your function's not defined at 1, so you had to do, yeah, that's both of those are convergence divergence ones. Okay, so there's going to be 2 out of 6.6. And then 7.1 is areas, right? Areas between curves. So I'm going to make sure that you can find the area between 2 regions with dx formula and dy formula, right? So you have to be able to go both ways and draw pictures, show me the rectangle, label it. I mean, I'm expecting some detail in this. And then that's it for 7.1. Wait, you'll have, yeah, 7.1 is the region, so you'll have at least one dx1 and one dy1. I'm trying to keep the number of problems down. This is a lot of material. So yeah, I know, and that's a lot. And then 7.2 is your volumes, your solids of revolution. So I would expect, again, it's going to be a region. It's going to have to be rotated around 3 things. So I'll give you a region. I'll say formula for rotating around x, formula for rotating around y equals 2, y equals -5. So just so you can show me the demonstrate the differences between rotating around different lines. And then we'll do the same thing the other way with dy's. I think I'm throw a bonus on the test for one of these. Yeah.
So it would be like x and then x equals 2 and then y equals
So it'd be 6 on that one? Or A, B, C?
Well, one where you have a region that has to go around the x-axis, around some other line like y equals -2, and then another line up here. Because you've seen how like the line being on different sides of the region changes the formula. So I want to make sure you kind of connect that.
The same problem.
Yeah, it'll be the same problem, and it'll just be like these 3 things.
That'll be 4 problems?
Hmm?
6, 3
No. It'll be one of each, 3 parts to each, so it's like 6 different integrals. Now keep in mind that on all the integrals for the solids and stuff and the areas, chapter 7 stuff, you're not going to have to evaluate them. I'll just say set up the integral, do not evaluate, but you'll have to take it home to evaluate it. On chapter 7 problems, areas and solids of revolution, you only have to set the integral up. You don't have to find the antiderivative, plug in the limits of, you don't have to do any of that on the test. But after you turn in your work, you take the test home and you finish that. It'll be part of the grade. Yes, it'll be part of the grade for the test. Not a huge part, but a part, like 10%. A letter grade difference. Okay?
I have a question. Say you get the integral wrong, but you work like the stuff in it right. Does that give you like partial credit, or
What do
do
you
you
mean?
like
Like,
say you get the integral set up and you start like solving it, and you get it like the integral's wrong, but you solve it right for what it is? Is that partial credit?
at home, you mean?
Yeah.
Yeah, that's if your integral was incorrect, but you went home and you did it all based on your incorrect, that's okay. But what I would expect you to do is go home with the problem and make sure it was right, and then base your answer. Because I will penalize you something for not being right. But if the work was right, it's you get credit for it. But if you, let's say, turned it in, it was wrong on the test, went home, realized you made a mistake, fixed it, and did it right, that's the way I'd like to see it done.
Okay,
You
but
know,
like just
you'll get
you
something
don't
for it.
notice that it's
Yeah,
wrong.
you'll get something for it.
Okay.
Yeah.
Great.
Are you teaching
Cal 3?
I am not in the summer.
Fall?
I don't think in the fall, most likely. I don't know. I don't want to say not summer. I taught it, I think, last summer.
I can't take it this summer.
Yeah. Most likely in the fall. Yeah. We haven't done our fall schedules yet, though. So okay.
Are you gonna do math intensive or no? Is it just certain people that do that?
Yeah, it's certain people that do those. Yeah. Are you wanting to get into that?
I was gonna get into the MEMS program and
Okay.
Cal 3,
Okay.
but I didn't know if you were gonna teach it because I do enjoy your class. So
Well, let me tell you something.